welcome to everyone. And now GTS NX, so it's like a complete geotechnical package. It's like a finite element method which is being used in this software, and all types of your geotechnical and tunnel engineering problems can be easily dealt in here. So you can find the same in the name itself. So GTS NX is standing for Geotechnical Tunnel Solutions New Experience. So basically, it's like a finite element method, and since most of them are familiar with the finite element method, I will be giving a very brief introduction and the workflow related to finite element method and how my presentation will correlate with that. And yeah, so coming to yeah. So this is our basic agenda for today. I will be giving you a rough idea about the software and rough idea about the company. The first agenda is to have a company introduction, and then I will be introducing you GTS NX and what are the modeling and analysis features in GTS NX. And then I will be giving you a rough idea about the project application. So there are many projects that has been done using MIDAS GTS NX, and then I will be giving you a rough idea about them. And then we will be going for software demonstration. So I'll be demonstrating some relatable models in this webinar so that you can relate with them. And then once this session is completed, whatever queries which you have already posted, I will be answering those questions. So about the company. So we, as a MIDAS, we started in South Korea, and now we are like the #1 market share in the entire civil engineering software solutions. So we are having like around 450 engineers and professionals, and we are like into 120 countries and 10,000 number of clients, and 90,000 plus licenses has been sold worldwide. And this is our global network. We hail from South Korea, so we are having our headquarters is at South Korea, and then we are having around like branch offices in USA, Japan, India, China, UK, and UAE, and these are all our partners. So all there are different partners in all around the world in around 90 countries. And so we started as an engineering consulting service. Basically, we started as an engineering consulting service, and then we gained knowledge, and we started our computer aided engineering technology and development department. Basically, this provided a synergy to provide optimal solution for practical engineering. So these are all our different product line. And here in building and structural engineering, we got MIDAS Gen, MIDAS D Shop, and Design Plus. MIDAS Gen is basically for buildings and the general structures, and the D Shop is it provides you with the drawings, and Design Plus is a design tool. And a bridge and civil engineering, we got MIDAS Civil and MIDAS FEA. So MIDAS Civil is for all types of bridges. So we can analyze and design most of the bridges in MIDAS Civil. And for advanced nonlinear analysis and 3D modeling, we can go for MIDAS FEA. And this is our basic area of focus today, the geotechnical and tunnel engineering. So in geotechnical and tunnel engineering, we got MIDAS GTS NX and the MIDAS SoilWorks. So GTS NX is basically a 2D and 3D geotechnical and tunnel engineering software. So it's the method used in here is finite element method. And in SoilWorks, it's like a complete 2D package where all types of our analytical methods, finite element methods, as well as limit equilibrium methods has been incorporated. So it is like a complete 2D package. And even in mechanical engineering, we got MIDAS NFX and MIDAS FX Plus. So this is all about our product line. And now coming to the most important and most focused area for this session, that is introduction to MIDAS GTS NX. So basically, this is a finite element software, as I was telling, and in any finite element softwares, we got a particular workflow which we need to go through. So let's say in any geotechnical software, what we basically do is we are having a geotechnical investigation team. So they provide us with the raw data, and then we go for that borehole data and experimental data produced by them. So we use those data to go for a geometric modeling. So the very first step in any finite element software is a geometric modeling. So in the geometric modeling, we use the bedding planes data or borehole data given by the investigation team, and we form a layers, and we form the majority of your site conditions. And then the second step is the material definition. So basically all types of your layers which is having different n values and different like unit weights and different elasticity modulus will be taken, and we will be directly going for input materials. So once the materials is getting inputted, we go for property definition, and then that will be followed by meshing. So your complete solids will be assigned with those materials, and then we will be dividing it into finite elements. So once it is divided into finite elements, that is nothing but meshing, we go for loadings and boundary conditions. So any type of loadings, the static loading or dynamic loading will be applied onto your structures basically. And then we go for analysis. So the type of analysis chosen will be depending on the problem statement. So there are many types of analysis, and we need to choose a particular thing for your problem statement. So, and then that will be followed by extraction of results. So this is a basic workflow in any finite element software, and GTS NX is no exclusion from it. And so based on your workflow, my presentation is on the same line. I will be starting with the geometric modeling. I will be going through the properties, definition of materials, and meshing, and I will be going for analysis and the result extraction. So this is a basic work line for this presentation. And yeah, getting back to our first major thing, that is your geometric modeling. So all types of geotechnical problems based on geometric modeling can be categorized under three things. One is axisymmetric modeling, another is a 2D modeling, and another is a 3D modeling. So all these three types of modeling can be covered under one tree or one platform, that is MIDAS GTS NX. So you can perform both your 2D, 3D as well as axisymmetry in GTS NX itself. This is how the interface looks like. You can find in the very top there is a geometry. This is a geometry. So what we do is all types of your geometric commands you can find will be here. All types of AutoCAD commands has been incorporated. So basically we start with the geometry, and then we go for meshing. In the meshing we go for material and property definition as well, and then we got different types of commands illustrated in different analysis tabs. Here we got a static and slope analysis, we got a slippage and consolidation analysis, and dynamic analysis. Basically all the commands related to this particular analysis will be present over here, and then we go for analysis, results, and tool. So what we basically do is we start with the geometry, go towards right. So from it's a left to right policy once again. And here this is a work tree. So whatever works you do from starting to ending will be registered over here. So this will be very much helpful if you want to change or edit it at any point of time. So this is our work tree, and you can find the icons are designed in such a way that with little glance you can find what that particular icon is meant for. And you can see this is a complete a product of GTS NX interface, and it is all similar. You can find this is similar to all types of our other MIDAS programs like MIDAS Civil or MIDAS Gen. And the very first step, as I was talking, is a geometric modeling. So what are the features and modeling capabilities in this MIDAS GTS NX will be explained to you now. Yeah. So this is a geometric modeling. Let's say there are many types of methods in order to model the condition. So now let's say we got one particular method. What we use the work plane, we model it in the work plane, and then we extrude for the 3D structure. Or else we can directly go for three coordinates X, Y, and Z, and we can go for modeling. Otherwise, we have a different VZs in order to model the feature itself. So basically all these will be easily to simulate in GTS NX. So what we do is we have a work plane, we model it in the work plane, and then we extrude it to form a to form a complete 3D solid. Otherwise, you can go for X, Y, and Z in order to form a solid itself. So that's nothing but X, Y, Z coordinates. Both is possible in GTS NX. You can find all the features are very similar with the AutoCAD commands. So most of the AutoCAD commands has been incorporated in here. And let's say we have a tunnel which is changing its direction along the length. In order to model this particular condition, we need to have all the coordinates in X, Y, and Z, and which will be very tedious for an engineer. And what we can do in here is we can have a profile, that's your cross section, and then we have a guide curve. So this is my guide curve, which is representing the direction and length of my tunnel. So when we have this guide curve and profile, that's nothing but your cross section. By using sweep option, we can have this particular tunnel generated within no time, not even a minute. So this is how we rigorously develop the different types of modeling commands present in GTS NX, and how that will be helpful for easy modeling and ease of usage. And you can find most of the other commands like trim and divide, and like you are cutting off your solid using planes, and the Boolean operations very similar to AutoCAD itself. And I will be explaining you this Boolean operation now. Yeah, so basically, in order to find a good contact with your one solid, two different solid, what we can say is there will be like number of layers present in the geotechnical model, and there will be number of solid parts. So one part should be in contact with the other part in order to have a complete stress transfer or complete the nodal connectivity. Basically, it should have a nodal connectivity so that the stress would get transferred. So in order to have a nodal connectivity, it is very important to use the Boolean operation. So for using Boolean operation for each and every solid, it's very tedious job. So what we got is we have a complete automated option called auto connect, which uses a Boolean operation for all types of your solids and all the solids present in the model. So with a one click, your entire solids present in the software, present in the model, will be interconnected with each other. So that's how important it is. So that is when we can find the nodal connectivity, and that is when the stress from the one solid can be transferred to the other solid. So that's why this auto connect option is very important, and this has been automated in GTS NX. And let's say we are having a piles, and we are having an anchors which we are interested in order to have a 1D element for it. So we draw a line, and how this line is made to be in contact with the solid or a surface. For that, we got an imprint option. Again, this is also automated. So select all your solids and select all your lines. With the one click, your complete lines, that is 1D elements, will be interconnected or with your solids or surfaces. So that's simple it is. And so as I was talking, there are many modeling features in MIDAS GTS NX. So this is one among them. Here we got a terrain geometry maker. Suppose let's say this is our terrain, like very complex terrain. This is a plan, and in order to model this particular feature, let's say this is my hilly area. In order to model this hilly area, it would be very difficult for an engineer, because it is very difficult to have the coordinates and points from all along the data. So what we do to overcome this, what we have is we will take the contour map of this particular area. So this is my contour map, and using this contour map, we develop a surface. So using this surface, this is a surface that was developed using terrain geometry maker, and using this surface we develop the model. So this is like a very simple, and which completes within like a 2 minutes. I will be showing you demonstrating this particular terrain geometry now. And what happens in here is, now you got a surface, and this surface is nothing but a complex terrain, but it is only a terrain. And how about your bedding plane strata? So this bedding plane cannot be uniform in all types of conditions. It should be varying, and it will be varying it throughout in many of the conditions. So in order to find this bedding planes data, we generally carry out the borehole data. So all the borehole data which has been obtained with the investigation team will be directly imported into a wizard called bedding plane wizard. So in this wizard, once you import all types of your borehole data, it will be forming at this particular surfaces. So this surfaces and this surface will be mixed and resulting in this particular model, which is a very tedious job for an engineer without using the contour map or a bedding plane strata, because modeling is a major thing in any finite element software. Once modeling is completed, the rest of the thing is a procedure. We go for material definition, we go for meshing, we go for loadings, and we go for analysis. So that's a procedure, but the modeling is the majority of the main thing. And now I'll be demonstrating you about a particular modeling feature called terrain geometry maker. So let's see. So let's say we are interested to model this type of terrain, so that after getting this particular terrain, I would be interested in like slope stability analysis, basically a landslide analysis, because we are modeling a 3D terrain. Or else I will be interested in a seepage analysis. Or else I will be interested in a dam construction over here. So once a dam is constructed, you will be having a reservoir. So I'll be providing it in the form of water level, and what is the seepage forces, what could be the stress analysis. So we can go for a further study once you got the model. So I will be showing you on how to prepare this particular model. So when you just click on the new tab over here, it will be asking you to choose among the three types of model types. It might be a 3D modeling or 2D modeling or axisymmetry. So let's say I'll be choosing a 3D as of now. So now it's a complete 3D modeling can be done in this thing. And here we got a terrain geometry maker. So what I do is I will open a terrain geometry maker, and I will be having a new tab developed like this. So into this new tab, what I do is I will import the contour data. Go to contour, and here I'll be importing a contour data. Let's see. Yeah. So this is my contour data, and I'm only interested in like a terrain. I'm not interested in the visible, like the boring data as of now. So this is my contour data. Yeah, this is my contour map. You can see this is the X and Y the axis, and this is Z and Y. So now what I will be doing is I'll be selecting all the area of my interest. Let's say I'm selecting all the contours, and I need to like make sure that from which end to which end I'm going to model. And let's say here this is a number of sampling points. Basically, in order to have a more accurate conditions, we need to go for more number of your sampling points. Let's say the maximum is 200. I'm going for 200. Yeah, so you'll be having something surface developed like this. So now the next thing is how we need to export this surface into GTS NX. So go to your export of your surface. Now I'll be saving it in the desktop. So once it has been saved, we need to import it into GTS NX. So what we do is so it has been saved now. We go into Terrain Geometry Maker tab. Once again, here we got import TMS file. So once you press on your trial TMS, it will be directly imported into the software, and it will be shown as a surface in here. Yeah, it's getting imported. So you will be having a surface developed like this. So you can see all the undulations present in your particular area, which is having a contour map. So you will be developing this model using contour map, and you got your all the features. So let's say we will be developing a solid out of this particular case now. I'm going for a work plane. So let's say I'm using a work plane instead of coordinates as of now. I want to develop a model from here to here. So I'm choosing a rectangle, and then I will extrude that rectangle. So we got an extrude option. So this is a direction to of my extrusion. That's a Z direction, let's say. And what is the length of your extrusion? Let's say I'm extruding it for 200. So just preview it. You can see that your solid is being formed, and then press OK. So now we need to divide this solid using your surface. Let's say this is my solid and this is my surface. And then just press just select your tool. So once your tool is getting selected, what you need to do is you need to just delete the above command, above solid, because you're making a complete solid, and then you need to divide it with the contour map, which is being imported from a terrain geometry maker. So now it has been, the thing has been cut, and we just delete the upper part. So we have a solid something like this. Let's say I'm interested in dam structure. I will be constructing a dam structure and I will be having a reservoir condition. I might run a seepage analysis. I might run a stress analysis. I can go for construction stage analysis. So any type of analysis can be chosen because the model is made now. And this is one thing, and or else we can directly go for a slope stability analysis. So because we are running and for a landslide in this case, so we can go for any type of analysis. That is all up to us once the modeling is done. So getting back to the presentation, so this is a part of one of modeling features, and we will be seeing the rest of the features present in GTS NX now. And yeah, I was talking about the bedding planes data, right? So using all the borehole data which has been imported from your Excel sheet, it will be developing surfaces like this. So it will be interpolating between the between two boreholes which is not having any data. So your two borehole data will be directly imported, and in between it will be interpolating and forming this type of surfaces. And so in any in any geotechnical model, the main thing we are concerned about is soil structure interaction. So we are having a pretty good features in soil structure interaction. So one thing, this particular features will be very much helpful to you in two ways. Like let's say you're having a like your structure, the building structure or a bridge structure, and you would like to run the analysis, and you would be producing a stiffness coefficients, and you will be exporting it to your structural engineers. So basically, we are concerned for two cases. One is production. All the geotechnical engineers are concerned for two cases in order to produce the stiffness data and to give it to the structural engineers. And the second thing is we are having a building, and very adjacent to it there is like a lot of excavation being done, or underneath it there is like a tunnel that is being excavated. So what could be the effect of your tunnels or excavation processes onto your existing structure? That is second case. And the first case is production, like generating the stiffness soil springs basically, because most of the structural team will be asking the geotechnical team to provide us with the stiffness data. We can go for design of our structures. So now, as I was talking, we are having MIDAS Gen, which is a building and a general structure and a general structural tool, and civil is a bridge engineering tool. So what we do is we will directly import all your model that is present in MIDAS Gen or MIDAS Civil into a GTS NX. So in here, we model soil as a continuum. We are not modeling the springs in here. We are modeling a continuum soil. Once the soil is modeled, what we do is we run an analysis and we produce with the springs. So all the loadings will be applied, analysis will be run, and we will be knowing the force versus displacement data. So which is most important thing, and that force versus displacement data at each and every node will be transferred back to your MIDAS Gen or MIDAS Civil, where it will be acting like an year of spring. So this spring data will be directly transferred to your your structural engineers, where they can go for their building analysis and design. So that's the stiffness conditions which we are going for. And the second case is I was talking about what could be the effect of your excavation or tunneling onto your existing structure. So what I do is I bring the structure back to GTS NX, and I will model the soil as a continuum as I was showing in this picture. And then very adjacent to it, I'm having an excavation. So I dig the soil in different stages. So when after digging, and at each and every stage, there would be a settlement, which might be a differential settlement, or that is posing a very great impact on your existing structure, which should not happen. So we need to go for stabilization techniques like provision of secant piles or provision of sheet pile, or all the like all the different techniques. Even that can be directly modeled and analyzed using this particular software. Now I'll be showing you one particular example where I have modeled a complete structure in MIDAS Gen, and I have imported that structure into GTS NX. So this is your model. This is a 29-story building. This has been completely modeled in MIDAS Gen, and I have imported that structure to MIDAS GTS NX. And in here, I was concerned about the tunnel, because what could be the effect of this tunnel onto my existing structure. So this is my existing tunnel, and I would be excavating this tunnel, and what could be the effect of this tunnel on my structure. So let's see. I have analyzed it, and I will be showing you results now. So there are like around 60 stages of excavation. Each stage will be like a 1 meter or 2 meters of soil will be excavated, and then we will see the difference between the results in each stage and what is the effect of this onto your existing structure. Let's see the settlement values now. So we got a displacement in here, and let's say I will be interested in settlement. So in Z direction, as per your global axis, that is my settlement. And now I'm having the settlement in the last stage. So let's say I'm interested in settlement from starting to ending. You can say the excavation is being started now. It started, so it is being proceeded. And as in how this excavation is going through underneath the your structure, you can see there is a change in the contour color of your structure, which indicates that there is this building is being displaced by some amount. And in order to extract that data, we have different commands. You can extract the data, and it might be a differential settlement. So take that data and provide some shotcrete or rock walls to your tunnel, so that that tunnel will be now very safe, and your building will also be very safe. And again, we can analyze that data as well. And you can actually take this video and you can present it yet in your presentations or report. So this will be more attractive feature. And let's coming back to a presentation. Yeah, so as I was talking, we are having particular feature, particular workflow in any finite element software, and we are done with the geometric modeling. So once the geometric modeling is done, we are having data of material from or experimental data from geotechnical investigation team. So the team is providing you with the data. So we need to define the materials in the software now. So the second step is material definition. So in this software, we are having materials like for elastic materials are present. There are many plastic materials, and there are some viscous materials as well. And we are having undrained conditions and unsaturated properties as well. So the most popular moculum is present in the software. We got in the plastic materials. Moculum is like a linear elastic and a plastic material. And in order to have even more non-linearity, we got a modified moculum, and this is your modified moculum, which is non-linear elastic and a non-linear plastic. Even that is present in the software. And for the clays, we got modified cam clay. And for rocks, we got hook bron. So you can see in for rocks, we got generalized hook bron and normal hook bron. And for liquefaction analysis, we got modified UBC sand. And for viscous analysis, we got these two materials. And let's say we also got hardening soil as well. So basically, in a retaining structures, what happens is at a low strength, the soil will be having high stiffness, and at high strengths, it will be having very low stiffness. In order to simulate that conditions, we got a hardening soil as well. Yeah, and these are all the different conditions that needs to be that has been developed till now, and which all has been incorporated in the software. And this is your user supplied material. If you're having your own material, you can directly develop that material in the Photon language, and you can directly bring in this user supplied material, and you can directly apply that material to your soil, and then you can proceed for analysis. So that's your user supplied material. And so these are all the different materials present in the software. These are all your constitutive material models. And apart from it, you can go for your undrained conditions and or a drained. So you can see the undrained conditions like effective stiffness, effective strength, effective stiffness, undrained strength, undrained stiffness, and undrained strength. And apart from this, we are also having unsaturated property conditions. So you can say this is like unsaturated properties. So even this can be applied for your soil conditions. So now the material has been defined. So that material needs to be applied for what property? It might be a 1D property, 2D property, or 3D property. So let's say I'm defining a material of concrete, and that should be applied for a beam element. So I'm having a 1D element, a beam element, a truss element, embedded truss element, even a geogrid element is also present in the software. And this is a 2D. Suppose we are interested in a 3D modeling, and I would like to go for generation of a 2D is like a geogrid in layers. So I need to go for geogrid 2D. So we got a geogrid 2D, gauging shell, normal plate or shell element, and we got plane stress and plane strain elements. So these are all our 2D elements. and this is a solid element which is a 3D. So basically in solid we got tetrahedral elements, we got hexahedron and pentagonal elements as well. So we got all it present in the 3D solids and some applicable elements like this. And the most important thing for soil structure interaction is, let's say there is a structure made of concrete and there is a soil which is having very low stiffness. Like basically when compared with your concrete, the soil will be having very low stiffness. So whenever there is a contact between high stiffness material and a low stiffness material, you can find a frictional force developed between those two materials. So in order to simulate that frictional force or tangential force, we need to develop an element called interface element. So this is our interface element. In order to have a very realistic condition, we need to go for interface element, and even that is present in the software. And apart from this, we got a rigid link and we got a pile tip as well. In order to know the end bearing resistance of your piles, you provide your pile tip and you'll be having the end bearing resistance, and provide with the pile. So this is a pile 1D element, and you will be having the skin friction data as well. From top to bottom, what is the variation of your skin friction, because we are having a different layers as well. So what could be the skin friction and what could be the pile end bearing resistance. And so these are all the other applicable elements which will be very much helpful in order to have a good analysis and good realistic analysis and good results extraction as well. So now we are done with the materials and we are done with the properties as well. So now we will be proceeding for the next step where we mesh the complete geometry. So these are the different tools present in the meshing. We got our 2D AutoMesh. Since 2D modeling is also can also be done in here, we need to go for 2D AutoMesh, or else we got a 3D AutoMesh and 3D map mesh. Basically what map mesh meant is, even for a very complicated structure, if you would like to go for a uniform meshing throughout, then we can go for 3D map mesh. And we got a very good feature in here called auto connect, as I was talking earlier. But because of this auto connect, what happens is, if there is like a very like this particular case, we got a tunnel in here, and because of this tunnel there will be like huge stress concentration at that particular area. So what software does is, it will be having very fine mesh in here. So that means a very fine mesh will be developed in the where we are having very high concentration of stress. In that case, a fine mesh will be developed, and towards the boundary it get coarse. So basically this type of conditions will be automatically considered by the software itself. And let's say we are modeling for a 2D condition, and once the 2D modeling is done, I would like to proceed for 3D in the in between. In the interim period, I would like to, I think, and I want to consider my 2D modeling as a 3D modeling, and I would like to apply loads, and I go for analysis. So what you can do is, for the mesh that has been generated in 2D, you can extrude it into a 3D, and you can find 3D elements, and you can run for the analysis. So that's simple it is. There is like a compatibility and change, and you can change from 2D to 3D at any time. And as I was talking, these are the different elements present in GTS NX. Apart from that tetrahedral, we got hybrid mesh. So what this hybrid mesh is, this hybrid mesh is a combination of your hexahedral elements, tetrahedral and pentagonal elements. Basically, this hexahedral elements will be having very great accuracy in results, and it will be producing very good results. So an analysis time will also be very slow, because the area covered by the tetrahedron will be very low when compared with the area covered by the hexahedron. So since there are a huge number of nodes, the accuracy will be very high. Here you can see this is a results developed by the tetrahedral element, and when you use hybrid elements, the result will be very smooth. The contour is smooth, you can find it in here. So basically when we use hybrid mesh, your time for analysis will be very low and your accuracy will be very high. So that even that is present in the MIDAS GTS NX. You cannot find this hybrid mesh in most of the competitive softwares. And once you're done with the meshing, we need to provide some loading conditions to it. So let's say, what are the different types of loading conditions that can be provided in the software? We will see it now. We can go for static loadings, we can go for dynamic loadings. So in the static load, we can go for a force, a concentrated load, a moment, a concentrated moment basically, and a displacement. I would like to apply displacement, a prescribed displacement of 50 mm, let's say. So I will apply a 50 mm, and corresponding stresses in the structure can be seen. And I can apply a pressure load. even a water pressure, and a temperature load as well. So basically, this will be very much helpful in a cold areas, cold areas where temperature load plays a key role. And if you're interested in anchors and rock bolts, in that conditions, if you want to provide pre-stress in your anchors, we can go for pre-stress in anchors as well. And you can combine all the loads that has been developed till now. And we can, in the dynamic loads, you can go for response spectrum, you can go for a blasting load, you can go for a seismic load, you can go for the machine loading conditions, we can go for blasting, as I was talking earlier. And here, for all the cases, we need to run a dynamic analysis, and we can go for either response spectrum, we can go for time history analysis, and all the respective analysis. So basically, we also have a train dynamic load table as well. This will be very much helpful in case of projects related to high-speed railway lines. Here we can see this is a blasting dynamic load. I'll be explaining it in the next slide. Yeah, here we can see I was talking about the blasting load, and there are many equations present for in order to develop a time history data because for the blasting load. So here in the GTS NX, we are having a particular equations for blasting load, and that has been already incorporated in here. And using these conditions and using the respective parameters, this software develops a particular graph like this. So this is my particular graph, and this graph is nothing but my force versus time, or else my acceleration versus time, or my normalist acceleration versus time. So that might be pressure versus time as well. So this graph will be applied at a particular point of my blasting. So once the blasting is started, what is the effect of this blasting on my adjacent structures can be carried out very easily in here. So how much my adjacent structure is going to get displaced, and what is the stress concentration at that particular point. So you can find the rest of the studies can be done very easily. And this is about train dynamic load. Since with the advent of this high-speed railway lines, we can no longer consider this soil like a load coming from the train as a static load. We need to consider them as a dynamic load, because train dynamic load is such a type of load which varies with the time and which varies with space as well. So in order to generate a time history data with this particular kind of train load, we need to have an data regarding to your train and data regarding to your velocity as well. And again, using this data and to develop this particular graph, which will be very much tedious for an engineer. So what GTSNX has given him an option is, this is a train dynamic load visit. Just provide your time, train velocity and type of your train, and GTSNX will be calculating the velocity. So based on the velocities and train type, it will be calculating the acceleration versus time, or a force versus time. And this is your acceleration versus time, and this is with respect to space. So with respect to time and with respect to space, it will be calculating the data. And once you get the time history data, you can apply it from one point to another point. And once the analysis getting started and completed, you can find the results like this. So what is the effect of your train dynamic load onto the existing embankment, or to so that we need to go for a concrete lining underneath the it means apart from the ballast or what we use in a regular conditions, we need to go for concrete lining, or that we need to come to the conclusion, because not even 1 mm of differential settlement is allowed in case of train rails. So that's why we need to run this train dynamic load rigorously for a upcoming dynamic load upcoming high-speed railway line projects. And this is a tunneling and anchoring visit. And here we can see, so let's say when we are having a tunnel, which is a very simple tunnel, and which is a simple tunnel, and there is no complications like intersections and cross tunnels and all that cases. In that case, it will be very easy for an engineer to model this particular tunnel using this tunneling and anchoring visit. So what happens in here is, we are not modeling the geometry in here. We are giving properties of your tunnel conditions in here, like what is the radius of here, is it a horseshoe tunnel or it is some other type of circular tunnel. So we will be providing the dimensions, and we will be providing the rock bolts and shotcrete data itself, and the excavation process and how the excavation is commencing. Is it commencing from the start and ending at the same time, or else is it commencing only from the start, and what is the length of the excavation in each stage, and then what is the mesh size. So just provide all the input data in here, and your software will be calculating the mesh size, everything, and it will be developing a model by itself. This is how strong it is. It can develop the model by itself by the data input, and this is your tunnel and anchoring wizard. So for a simple tunnels, it will be very much helpful, and but for a cross tunnels or intersections, when you're having this type of conditions, we need to go for a direct geometric modeling, the followed by our general conditions like materials and meshing, and then loading, and then analysis. So now we discussed till now we have discussed till using what are the different features in geometric modeling, and what are the different features in material conditions, what are the different features in like properties and meshing. So you're done till here, and then you went for loadings as well. So now we need to run the analysis. So what are the different types of analysis GTS NX can offer you? Yeah, this is the answer. So you're having different types of analysis for static cases, for dynamic cases, and all the rest of the conditions as well. So let's say if you want to run an static analysis, so we can consider a linear static analysis or non-linear static analysis. So both this can be performed in GTS NX. And when we go for slope stability, so there are different methods like limit equilibrium methods present in different softwares, but this is a finite element method. What we choose is we choose a strength reduction method. So this strength reduction method is a technique which calculates the factor of safety in order to have for a landslide analysis or a normal general 2D slope stability analysis. So that's the case because this SRM technique is applicable for both 2D and 3D modeling. And we are also having another method called strength analysis method, SEAM. So this is a combination of both your finite element method and your limit equilibrium method. So all the slip circles will be taken, and all the like uh, the failure surface will be calculated based on FEM, and the slip circles will be incorporated. So basically the stresses will be calculated from using FEM, and the failure uh, surface will be developed based on limit equilibrium method. So that's a strength analysis method for you. And this is a strength reduction method which is widely accepted throughout the world. And we can run this in a construction stage analysis as well. And in the dynamic analysis, we can go for eigenvalue analysis, we can go for response spectrum analysis, and we can go for linear and nonlinear time history analysis as well. So all these can be performed in GTS NX. And apart from this, we are also having 1D ground response analysis. So basically this 1D ground response analysis is very much helpful in order to know the dynamic properties of your soil. So even that is present in the software. So once you just provide the layered conditions and run the analysis, it will be providing you with the damping ratio. It will be providing you with the converged shear modulus. So once you get the dynamic properties, you can apply them to your general structures, and you can go for time history analysis or response spectrum analysis. So that's how strong GTS NX is in the dynamic analysis. And it is also having a coupled analysis with a strength reduction. So what we do is the nonlinear time history plus SRM coupled. Suppose there is a like hilly area, and we are going for seismic analysis. So we apply seismic conditions, and then we go for seismic analysis. And once the loading is completed, what is the factor of safety of the like displaced model? It's because it has been covered with the seismic loading. So after the analysis, we can go for the strength reduction method, and it will be providing you with the factor of safety. So basically your dynamic analysis is coupled with the slope stability analysis, and we can find the factor of safety accordingly. And apart from this, we are having a seepage analysis. In the seepage analysis, we can go for steady state seepage or a transient seepage analysis. And apart from this, we are also having the stress seepage fully coupled analysis. So basically what happens is in most of the like limit equilibrium conditions, we cannot consider the variation in pore water pressure in our analysis. We only consider the external load, and we consider just water condition, so whether it is saturated or not, and then we run the analysis. but we are not considering the variation in pore water pressure. So in order to consider that one in finite element method, we need to run a fully coupled analysis or a semi-coupled analysis. So this is your semi-coupled analysis. This is your stress seepage analysis. Basically what happens in here is in the first stage we run a seepage analysis. So we will be knowing the variation in pore water pressure with respect to time if it is a transient analysis. So once we get that analysis results, we will produce that results in the second stage where we run a stress analysis and a slope stability analysis. So basically you're considering your pore pressure variation with respect to time, and you're applying it in the second stage where you're running a slope stability or stress. So you're considering the effect of your seepage. So your factor of safety will be very low when compared with the factor of safety in a dry conditions. So that's what we can infer from a finite element methods, and we need to run a stress seepage coupled analysis in order to get that particular results. And apart from this, we are having a consolidation analysis. So this consolidation analysis, you can find the results such as a very settlement with respect to time and pore water dissipation with respect to time. So you can find that in the consolidation analysis. And once we are done with that, if we are going for a stabilization techniques like a stone columns or sand compaction piles or plastic board piles, what we do is we just simulate that conditions, and using that conditions we can even find the results like a stress your with respect to time, what is the settlement and your pore water pressure. So even the stabilization techniques can be applicable in GTS Annex, and you can perform consolidation analysis for the same. And in the construction stage analysis, so basically we need to go for the construction stage analysis in most of the conditions, because soil is such a non-linear material, and as the stress changes its behavior changes. So in order to consider that particular condition, we need to go for construction stage analysis. And in this construction stage analysis, all the other types of analysis can be covered. So all the other types of analysis can be easily covered in construction stage analysis, and you can go for either stress analysis, either seepage analysis, either stress seepage coupled analysis, or a fully coupled analysis, or a consolidation analysis, or a dynamic analysis. Basically, all the other analysis can be like simulated in construction stage analysis as well. And now we are done with the analysis part as well. And now we will be going into the post processing. So that is nothing but extraction of results. So before going into that condition, I will be saying you some easy control options present in GTS NX. Yeah, here we are having automatical consideration of water pressure. So what it basically meant is, here you can find, this is my water level, and I'm having excavation that is being done. So because of this excavation, I will be having water level like this. So because of this water level, I might be having forces on the walls of my excavation. So what we basically do is we will calculate all the forces manually, and we will apply it on the walls. But in GTS Next, when you like enable the option called automatic consideration of water pressure, the software automatically calculates the pressure, and it will be applying it on the walls wherever there is opening underneath your water level. It will be applying the water pressure. So it will be applying automatically. And similarly, you can have, this is, let's say this is my water retaining structure, might be a dam, might be a barrage or a weir. And in this particular condition, I will be applying a water level in the upstream side, and I will enable that option. So what happens is all the forces will be automatically applied on the like my wall and the soil as well. So what basically applies is you'll be having the automatic water pressure as well as seepage force. Everything will be applied automatically. So that's the automatic consideration of water pressure meant for. And now we'll be jumping into the post processing tools. Yeah, so you can find many types of results in any finite element softwares. And what are those different types of results we'll be seeing now? You can find a flow paths for a seepage analysis in, and you can go for animation or your screenshots. You can find them. You can find the graphical results. You can find the contour maps. You can find the tabular outputs. You can find the text format. So basically, all types of formats will be obtained from this GTS NX. So let's say this is my tunnel. I am having a contour map of stress, let's say the vertical stress, and I would like to see the stress in the particular section. So I can cut the section, I can find the section like this, and I can see the results from top to bottom. Basically, I can probe the results. At any point of my interest, I directly go over there, I just click over the point and I can find the results. So that is the probing of results means. And here we can find a section diagram. What I can say is I will cut the tunnel and I will see the result of bending moment diagram. I can see the result of axial force at the particular section. Basically at the particular section as well, you can find this type of diagrams. So this will be very much helpful, because this type of results we get only in 2D analysis, but even in a 3D analysis, you can find this type of your section diagrams, which will be very much helpful in comparison study. And now this is your ISO value surface. So I will ask the software to show me the area of which is having a stress of 50 kilonewton per meter square, let's say. So I will provide the ISO value of 50 kilonewton per meter square in a stress. So software will directly show me the area which is experiencing the like a stress of 50 kilonewton per meter square. Similarly, I can ask the software to show me the displacement area which is undergoing the displacement of 12 mm or 10 mm or respectively. So this is your ISO value surface. And as I was talking about this particular text value, so this is your LDF sum, that is local direction force sum. Basically, in the solid elements, we never find the bending moment diagrams. We cannot find our axial force, all the cases, because we can only find stresses. We can find like displacement in here. So in order to find your let's say bending moment diagram even in the solid elements, we need to go for local direction force. We will develop a surface where I'm interested in order to find the bending moment, and then I will ask the software to calculate the bending moment in that plane, and it will be providing you with the text format. And let's say this is my model, complete model, and I would like to see the result at each and every point. So I will directly go and probe the results. So that's what we can do. And we can go for clipping like many planes as well. So here you can see this is like complete one structure, but I can clip the plane and I can go for union or intersection of two planes as well. And the most important feature is a 3D PDF report. Basically, we will find like huge number of results in an finite element software. So what we need to do is we can directly, what we do basically is we will generate the report. We will send the report to our higher officials or like your client in order to see and go through the results. But basically, we need to develop a report, which is again a tedious job. But what this software does is this is a 3D PDF report. We will directly take the entire model to a like 3D PDF. So how you handle it in the software, we handle the same it in the 3D PDF as well. So you can see the results like your stresses, you can see the results of your like a settlement, you can see the results of pile bending moment diagrams or axial forces of rock bolts axial forces. So all types of your data can be seen. You can see the measurements can also be done in here. So basically this is a 3D PDF report. It will be very much helpful if you directly generate a 3D PDF and it can be shared with the like your clients or your higher officials, so they can directly go through the model instead of going through the report. So this is nothing but a 3D PDF report. And now the next agenda, so according to agenda, the next topic is a project application. So I'll be giving you a rough idea about different projects that has been done, the different important projects that has been done in using MIDAS GTS NX. Yeah. So let's say this is a particular a slope stability. I'm having an like a retaining wall which is going to apply over there, and before the retaining wall, I need to go for excavation. So what I do is I will go for excavation in construction stage analysis, but I need to have like I need to have factor safety at each excavation, whether that excavation which I'm doing is safe or not, because if because of that excavation there might not be any failure surface, and what is the factor of safety accordingly. So we need to find them in different stages. So in one single model, what I do is I will excavate the surface and I can find the factor of safety and I can find the failure surface, and again I will excavate other case. So first excavation is done. What is the failure surface and factor of safety? Second excavation, failure surface and factor of safety. Similarly, third excavation I can find, and even in the fourth, last excavation, I can find a failure surface and along with the factor of safety. Basically, in one single analysis, you can find the factor of safety in each and every condition along with the failure surface, and you're even running a stress analysis basically. So basically, you're having all the slope stability analysis and the stress analysis running at the same time in a construction stage analysis, which is very important when we are going for an excavation in a very huge project. And yeah, this is one type of one of the project that has been done in GTS NX. So this is a power plant which I'm showing you, and this power plant is like vulnerable for like a landslide, let's say. So what they have done is they have like completely modeled the entire terrain using terrain geometry maker, and this is the complete model. And using this terrain geometry maker, they model and they have analyzed the initial condition. You can find this is the initial condition, the displacement contours. You can see most of the maximum displacement is concentrated in the bottom. So now what happens is my complete like a power plant is like completely destroyed. So which should not be the case. So what they went for is they went for stabilization by using step-by-step retaining walls. So this is the retaining walls, and they have simulated the same in the software. So this is the step-by-step retaining wall, and they had simulated the same, and they went for analysis, and now they found that the displacement is maximum only at the top and your power plant is safe. So basically we can go for all types of studies regarding your slope stability or landslide or your stress analysis, and you can find the results, and you can go for design. This is your movement vectors, and this is a failure surfaces. So we can find most of the failure condition in the initial stage, which should not be the condition. So we need to go for some stabilization, and in this particular project they went for step-by-step retaining walls. And in tunnels we can find this type of tunnels as well, two tunnels, and here we got a fractured zone. So we will be modeling that fractured zone directly in GTS NX and providing the respective parameters. And you can even go for two tunnels along with the shaft, and tunnels along with the cross tunnels, and these tunnels are having different cross section. So every model will be everything will be directly done in GTS NX itself. And this is where like this type of projects is like pretty common nowadays, because most of the governments are going for crude oil storage. So we can go for this type of conditions, and you can model the shaft, cross tunnels, two main tunnels, and your cross section, big cross section tunnels as well. And we can even simulate the TBM, the tunnel boring machine can also be simulated. Basically, all the tunneling can be excavated using three methods. One is your tunnel boring machine, and other is an NATM method, not New Austrian tunneling method. And we also have a drilling and blasting method. So all these methods can be easily simulated in GTS NX. This is your TBM method, and we need to go for NATM method here as well. And let's say we are having a bridge pier that is the existing structure, and we are having like a excavation in the form of tunnel. So we are going and excavating the tunnel, and what is the effect of this tunnel excavation onto the existing structure? So we can model it and we can run the analysis. So there is one particular project has been done in using this particular case, and I will be showing you that project now. And even you can go for shotcrete, we can go for rock bolts, and you can go for different types of bench cuts as well. So you can see the crown has been removed, which is followed by the lower part. So and then it directly goes further, so we can go for any types of cuts in the software as well. Yeah, this is one particular project. Here you can see there is like a terrain which is having a very complex terrain, and they have model using my terrain geometry maker. And this is your two tunnels along with the shaft. This is a tunnel which is has been done using completely MIDAS GTS NX, and here they got shotcretes and rock bolts as well. Now we will find the what are the different results they found. Here you can find rock bolts and the shotcretes present in here as well. So this is a complete picture of the model. And these are the displacement. And you can find shotcrete stresses. The most of the stresses is concentrated in the intersection part, which is pretty appropriate. And we got like a rock bolt axial forces. These forces can be again transferred back to your structural engineer for design. and of your rock bolts. And we can even go for driven piles. We can go for well foundations, foundation piers, raft foundation as well. And this is one residential project which has been done in completely in MIDAS GTS NX, and this residential project is located in Dubai. So what happens is what happened was they had completely modeled and the foundation by considering the friction piles. So what happened was because of this friction, only friction condition, they found the length of the pile is like too high. It is like 40 meters, and there are like 380 number of piles, which is going beyond the economy which they are having. So what they found is they want to go for like a pile raft foundation. So what have they have done? They have went for GTS NX and modeled the raft and modeled the piles accordingly. And now the settlement has been reduced because the load from the superstructure, 30% of the load is being taken by the raft itself. So because of that, we can find most of the like piles has been reduced with its size. It has been reduced from 40 meters to 32 meters, and you can find there are 380 number of piles, and and the reduction in length is 8 meters. So how much amount of concrete and steel has been saved? So we can go for this type of analysis in GTS NX by considering both pile raft foundation, and we can produce the results. This is your pile axial forces, vertical strains, and bending moment diagrams. And this is a diaphragm wall. And this is the tunnel subway line. Basically, we are having a subway line, and this is like it might be an excavation for your subway station or any other purpose. Even this type of conditions can be easily done in construction stage analysis in GTS NX. This you can find here. This is my diaphragm wall, and in the diaphragm wall, inside we can find a struts. We can find plus plugs, and we can find wallings on sheet piles, everything. So each and everything can be having its own section. We can provide that section to sectional properties to that particular elements, and we can run the NS, and we can find the results like bending moment diagram, the force acting onto the sheet piles, and your displacement. So all types of results can be easily seen in using GTS NX by running this kind of analysis. And modeling is like a very easy in GTS NX. And this is one particular project here. This is a high-rise building which is being constructed on like a sloping ground, because in India we sloping ground cannot, on the sloping ground high-rise building cannot be constructed. And this building is located in Monaco. Yeah, this building is located in Monaco, and it is having a 49-story building. It is a 49-story building, and they face many conditions for this 49-story building. So many problems. What happened is they would like to excavate the slope so that they can provide the foundation, and because of that excavation, it may pose many problems while analysis. So what while execution, what happens is there are like villas, high schools, and some major buildings around this particular tower. This is Odeon Tower, and because of that excavation, this particular like buildings can have a can is vulnerable for landslide basically. So what they found is they want to go for anchors and diaphragm walls. So this is the solution provided by them, and they have provided the anchors and diaphragm walls. And they found that all the settlement has been concentrated only at the bottom. So you can see the plastic zones which is forming only at the bottom, and there is like very less lateral displacement. And now there objective has been achieved. So they went and analysis, and they found that it is safe. So this is the vertical wall displacements and the plastic zones. And apart from this, we can go for a CFRD analysis. So this is your concrete face, the rockfill dams, the seepage analysis for embankment, the fitting waterway tunnel, underground driveway. Yeah, this is another project which has been done in Korea. Basically, this is my bridge piers, and this has been modeled in MIDAS Civil. I had completely taken that model back to GTS Enix, and very underneath it, there is like a new proposed tunnel which needs to be modeled and excavated. So, what is the effect of this tunnel onto the existing structures? So, they would like to study it in GTS Enix, and this is a plan and section of that particular model. This is a subwell, and when they need to dug the for tunnel. And what they found is they found the bridge pier is facing a differential settlement. You can find this is my displacement. So this is a pile cap basically, and here you're having more displacement in the other end, so which is not feasible. So they went for shotcrete, more like the thickness of shotcrete has been increased and the rock bolts has been produced even more higher, and they found that this particular like differential settlement is not arising now, and they found that complete model is safe. So you can find the shotcrete stresses, and you can find the like rock bolt stresses as well, rock bolt forces basically. And this is another project which has been done in Korea, South Korea. We got a Buhang Dam. This is a Buhang Dam, which is a completely earthen dam, and they modeled it in using complete GTS NX, and they modeled it in a construction stage. So in the first stage, there is an in situ condition. In the second stage, they provided a foundation. In the third stage, they provided a banking height of 100 meters, and they went and so on. So you can see this is the stages. We can have in second stage, we got a banking height of 160 meters. In the third stage, we got banking height of 210 meters, and we got a hydrostatic pressure as well. So the pressure applied on the upstream side has been applied. And here we can see this is the total displacement, horizontal displacements, vertical and hydrostatic pressure. So these are the results. We can even find the flow paths, hydraulic gradients, a flow rate as well. How much amount of water is being coming from upstream to downstream. So this seepage analysis can also be done, and we can find the flow rates as well. The total head can also be found. Yeah, so these are the different types of results which you can find in this particular project. And apart from these projects, we are having many different projects which has been done entirely in GTS NX. You can find these are the other applications using GTS NX. The upcoming Kingdom Tower in Abu Dhabi has been completely modeled and analyzed in GTS NX. So similarly, you can find the Dubai towers. These are the other project applications. Now I'll be showing you a brief introduction. So this is a brief introduction on the software, and now I'll be showing you some models. So let's see. So if you're having any queries, please post it in the query tab, questions tab. I will be answering these questions once the demonstration is done. Yeah, so let's say we are having very earthen dam. So this is my earthen dam. I have completely modeled it in GTS NX. So I have run for a stress analysis. I went for a slope stability analysis. I went for a coupled analysis in here. This is an internal curve which is having very low permeability, and this is the a dam casing, and the like lower part is a foundation, and or a subgrade. So based on the conditions, we can go for and we can provide the properties. And these are my filters. So this is my filters. And now we will see the results. You can directly model them using AutoCAD features, or else you can directly model them in GTS NX itself. So as I said, I have run a slope stability analysis. Now I'll be showing you the factor of safety which has been run, and using only stresses obtained from here. So the factor of safety which you got is like around 2.45. And you can find the displacements like this. You can see this is my displacements. And let's say I'm interested in the failure plane. Yeah, so here you can see this is my failure plane. This is my equivalent strain, so which represents my failure plane. And so what happens in here is you can see most of the like failure is going through the filters. So which is pretty obvious because filter is having very low stiffness, and which is vulnerable for failure. And now we will see the seepage and the flow rates and even phreatic line as well. So let's remember the value. We got a factor of safety of 2.45 for only slope stability analysis. And now I have run a stress seepage slope coupled analysis basically, because in the first stage I will run an seepage analysis. All the results from the seepage will be carried forward to the second stage where you're running an like a slope stability analysis. So now we will see the results for the same. Yeah, here you can see this is a stress seepage slope, and you got a factor of safety of 2.15. because in this condition I have considered the seepage forces as well. The factor of safety has been reduced from 2.45 to 2.15, which is still this is okay, because this is like satisfying the condition of 1.5 factor of safety. Suppose, let's say in this condition I have only considered the steady seepage, but let's say I'm considering the transient seepage analysis and I'm going for slope stability, then there might be some different, because in transient seepage you might be having sudden drawdown as well. And now in the this stress seepage analysis, coupled analysis, I'll be showing you the displacement data. It is similar. This is your settlement, and this is your horizontal and the total translations. This is your horizontal translation. And this is my failure zone. And now I'll be showing you the flow paths. So these are my flow paths. So at any point of your interest, you can directly probe the results and you can find the flow paths at that particular point. You can find that this is my internal core, which is having a very very low permeability. So that's why you can find the water is getting seeped and it is going from downstream to upstream to downstream underneath the internal core, because it is having very very low permeability. And you can find, since most of the filters that the data which has been provided for the filters, it will be having very high permeability, means it will be taking water from it and it will be like delivered to the downstream, because we don't want the like piping condition that needs to be formed. So you can see most of the the flow paths are going through the filters, so which is appropriate. And now I will just play a video so that we can find this type of results and we can just save them and you can present them at any point of time. You can see this particular flow path is going through the filter in the upstream, and it is going through here, and in the downstream it is just joining the downstream through the filter again. So the part of the filter means the part for which the filter has been designed is being executed now. Yes. So now let's say we are interested in like equipotential lines. So basically in the equipotential lines, we need to go for total head. Let's see. So before going into it, let's say we will be interested in finding a ferritic line. So on the ferritic line, my pore pressure head will be 0. So I'm going for 0. I'll just plot the result. Yeah, this is my ferritic line. You can find this is my ferritic line, and in the core you can find there is a sudden drawdown because the core, if it does not allows most of the water, but this is a ferritic line. And let's say I'm interested in showing values like equipotential lines, and you got hydraulic gradient. It means you can find the hydraulic gradients, you can find the velocities, the saturation conditions as well. Yeah, this is my total head, and I will just use the condition called fringe. So here, what this represents is this is representing my equipotential lines. I mean, where the total head is a constant value, so you can find the equipotential lines. And also you can go for flow rate as well. So this is the amount of water that is coming from upstream to downstream. You can directly probe the results, and you can come to know what is the value. Let's say I'm having very low value. I will be changing from meters to mm. So you can have this amount of seepage that is in mm cube, which is very low, mm cube millimeter cube per second. Now I'll be showing some another model regarding to pile foundations, let's say. So this is a very simple model, and I have considered two layers, soil 1 and soil 2, and this is my simple raft and having 4 piles. And these are my section properties. I'll be showing you the properties of my piles. Yeah, I just considered some rectangular piles. and this has been analyzed, and I will be showing you the results. I applied the pile tip at the bottom and even pile as itself as well, because if you go for a pile element, you will be finding a skin friction. If you're going for end bearing, you need to go for apply a pile tip basically. Now let's say I'm interested in finding the pile axial forces. So what we do is we go for beam element forces in here, and you just press on axial force. So in this particular model, I have applied the lateral load as well. So this is axial force, and you can find shear force along different directions, and you can find all along there, all along the depth, and even you can find bending moment diagrams. So this is element center results, or if you go for bending moment about Z, because in this particular model, I have applied lateral load as well. So that's why you can find the variation from top to bottom. And now I'm interested in skin friction, let's say. So I can find skin friction as such, and I'm interested in finding the pile tip force, which is nothing but end bearing resistance. Just double click here, you can find the values. So because these are at the very bottom, you can find the end bearing resistance. The maximum and minimum loads can be found based on the property of a soil present over there. You can find the end bearing resistance, and I'll be showing you the displacement contour now. Yes, this is how you can find the displacement contour. You can find something like this. You can actually probe at any point of your interest. And then, yeah, as I was showing you the forces, these are the different load combinations that has been given to here. So there is a like a vertical load, and there is a lateral load here as well. So this is a lateral pressure that has been applied. So you can apply at any point of your interest the lateral load or vertical load or concentrated load or moment directly on the piles as well. I was also telling about we can calculate the stiffness, and we can directly send the stiffness from like a GTS NX to the structural softwares. So this is one project of such a kind. Here, this is a building that has been completely modeled in MIDAS Gen, and these are the different soil layers. So what I'll be showing you is I'll show how to export the results. So just export your nodal results. So we need to export the result of your force versus displacement curve. Let's say I'm interested in the load combination. So this is a combination that I have been applied onto the structure. So for the same combination, I will be taking back the results. Here you can directly go and go for force displacement, and when you go for OK, you'll be having a text format, and that text format can be imported back to GTS NX. Sorry, imported back to your structural softwares. So that is how you can go. Now what I will be doing is I'll be showing you slope stability, the 3D slope stability basically. Yeah. Now just this is a mesh of the 3D slope, and the factor of safety obtained is like 3.4, which is pretty good. Yeah, you can have the results something like this. This is a landslide of that particular project, and yeah, you can find something like this. So this is the undeformed conditions. When we go for deformed, you have something like this. It is deforming very high. It means that like whenever there might be a failure, it may go up to the value of 62 meters. So once there is a failure, your slope can move up to a distance of 60 meters, which is a devastating condition. And still, but the factor of safety which you obtained is 3.4. As of now, it is very safe. But you can find the failure surface. You can find the failure surface like this. So this is how the displacement is being showing its condition. But whenever there might be a failure, it can go up to a 62 meters, and the factor of safety which you got is 3.48. And now I'll be showing you the results for a retaining system, the lateral support system, let's say. This is a complete model. In between, I'm going for excavation, and I have provided some lateral support. Just I will be showing you, that lateral support system now. So all the layers, I'm just hiding them. Yeah, this is a lateral support system. I will be just showing you the properties, the sectional properties as well. Yeah, you can see these are my plus plex, and these are my struts, and these are the wallings, and these are my sheet piles, and these are my anchors. So basically all types of your lateral support system can be easily modeled and generated in GTS NX. So now we will see some results. What I have done is I have removed each and every excavation set in the different stages so that I can find results in each and every stage. Let's say I'm interested in finding a displacement of in a last stage where the complete excavation is done. So you can find the displacement in the bottom. This is the settlement basically. If you're interested in a horizontal displacement in a x direction, in y direction, you can find them. And this is a lateral displacement. You can have a clip plane which is generated like this. You can go from one end to another end. Yeah, you can have something like this. So you can take the pictures of this one and you can provide it in the report, and even in the software itself we got an image file. So whenever you go to this particular command, the software takes the snapshots of your interest and it will be directly transferred back to this folder, and where you can directly take the snapshots or Word format as well. And this is one condition, and now I'll be showing you the results in the different lateral supports. So this is my plus plug, and these are my wallings, structures, anchors, and the sheet pile. Let's say I'm interested in axial force of the anchors. Now, in order to find the axial force, we got the truss element forces in here. You can directly go and provide, go check on the axial force. You can find the axial force coming onto your anchor. And apart from this, we can even find the bending moment diagrams, shear forces and axial force in the wallings. So because I have considered wallings, you can find the bending moment diagram in here as well. And let's say I have considered sheet pile as well. So what is the bending moment diagram on a sheet pile? Because I'm considering this type of a plate element or a shell element, you can find the bending moment in XX direction, in YY direction, in the form of a contour. Because wherever you find a lateral support, or you can find this type, we need to go for the bending moment diagram even for the sheet pile, so that if whether that pile is resisting the entire load or not, we can come to know. Lateral load and your lateral displacement can be easily found using this particular conditions. And now I'll be showing you another example of a simple tunnel. Yeah, in here you can see this is my entire tunnel, and this is my main soil. I'm just hiding the main soil. Yeah, and now I'll be simulating the conditions what has been done in here. So this is a simulate stage. I'll just show. So you can see the excavation is being done, and and you can find the shell, that's a shotcrete stress, a shotcrete, or your concrete lining is being activated, as and how your excavation is being done. Here you can see, and this is the construction stage analysis, and that's how I can represent the thing. Now we'll see the results. I will be going for a displacement. Let's say I'm interested in displacement along the Z axis, so that is nothing but my settlement. Yeah, you can find the displacements like this. I can probe the results. So 2.9 in the top, 2.7 in the bottom. So this minus represents that it is settling, this plus represents is heaving. So it all depends on the shotcrete and your adjacent element forces. So at any point of your interest, you can find the results. Yeah. So this is all for today. If you're having any queries, please post me the questions. I can help you through the answers with the answers. Or else you can post me the questions to harsha@midasit.com, or else tech support@midasit.com. You can post the questions and I can help you out with the answers. So as of now, if you're having any queries, please let me know.